Hi and welcome back. In the previous video we introduced triple integrals as a way to add together a density of a solid object in 3 dimensions. In this video we will focus on computing triple integrals. Just as we did for double integrals, we try to find a way to write a triple integral as an iterated integral. More specifically, we want to reduce a triple integral to first computing a single integral and then a double integral, since we know how to handle those kinds of integrals. For double integrals, regions which we called type 1 and type 2 turned out to be well suited to write a double integral as an iterated integral. For triple integrals, we will follow a similar procedure. We will discuss 3 types of regions, which turn out to be the natural equivalents of type 1 and type 2 regions in 3 dimensions. They will allow us to write triple integrals as iterated integrals. We call these regions type 1, type 2 and type 3. This terminology is not standard and you might encounter a different terminology in your calculus book. These are, of course, the same names as we used for double integrals, but from the context it will always be clear whether we are considering regions in 2 or 3 dimensions. A solid region is said to be of type 1 or z-simple if it lies between the graphs of 2 continuous functions of x and y. That is, we can write E as the set of all points x, y, z with z in between u1 and u2, which are both functions of x and y, while x and y take values in some region D. This region is the projection of the solid onto the xy plane. A projection means that we squeeze together a region onto the xy plane. It turns out that you can compute a triple integral over a type 1 region by first integrating over the special variable z, where the functions u1 and u2 are used as limits of the integral. The resulting integral is a double integral over the projection on the xy plane. So we can compute this using our known techniques for evaluating double integrals. The next type of region we consider is called type 2 or x-simple. Here x is the special variable because it is bounded in between 2 functions u1 and u2 of y and z. Meanwhile, y and z take values in the region D, which in this case is the projection on the yz plane. A triple integral over a type 2 region can be computed by first integrating the special variable x and then evaluating the resulting double integral in y and z over the projection D. Finally, in a type 3 or y-simple region, y is the special variable as it is bounded in between 2 functions of x and z. A triple integral over a type 3 region can be computed by first integrating over y and then the resulting double integral over the projection on the xz plane. As an example, consider the following function, which we want to integrate over the prism with sides y is 0, x is 0, y is 2, z is 2 and z is 2x. This prism is a region of all 3 types and we will view it here as a type 1 region. That means that we should find out in between which 2 functions of x and y the variable z can be bounded. Luckily, we can read this off easily from the picture and we find that z is bounded in between the functions 2x and 2. Now we should find the projection onto the xy plane. If we flatten the prism onto the xy plane, we find that exactly all values of xy in the blue rectangle are the ones we need. So the projection is given by the rectangles with sides 1 and 2. As such, we evaluate the triple integral by first integrating z from 2x to 2. Then we can compute the resulting double integral as we're used to, and you can see the result on the screen. Please pause the video to check these calculations. To conclude, let's consider what happens if the region is not of one of the 3 types we have discussed so far, such as this cylinder with a hole in it. In these cases, it is often possible to divide up the region into several parts that are simple. This means that we can compute a triple integral over a non-simple region by computing the corresponding triple integrals over its simple parts and then adding the results back together. In this particular case, it might also be worthwhile to describe the region using so-called cylindrical coordinates, but that is a topic for another time. That is it for this video. Next time we will talk about how we can use different coordinate systems to evaluate triple integrals, just as we used polar coordinates for double integrals. See you then!